Hello, and welcome to TI Precision Labs discussing board-level troubleshooting. Board-level troubleshooting is the first in a series of guides which will provide best practice application debugging techniques known as the Quality and Application Handbook. Various engineering checks are outlined to help determine the root cause of an issue. The first training focuses on a technique known as the ABA swap. In addition, an introduction of PCB parasitics and the importance of PCB cleanliness are reviewed. As discussed, the Application Handbook is a section of TI Precision Labs dedicated to troubleshooting and debugging. Various engineering checks will be presented, including the following topics but not limited to the ABA swap, PCB parasitics, PCB cleanliness, curve trace analysis, digital multimeter use, precision measurement techniques, power amplifiers and high-speed amplifier best practices, stability, and PCB design best practices. The examples presented can be applied to applications containing integrated circuits of varying complexities. Information discussed and presented within the troubleshooting guide is provided as is. The content is provided with the intent to assist in the debugging and analysis processes. The ABA swap is a critical troubleshooting technique highly recommended during the debugging process. The ABA swap helps to characterize how the application performs using various devices of the same model. In addition, the ABA swap technique verifies if the application failure characteristics follow the device under test. Device under test will be referred to as the DUT for the remainder of the presentation. Completion of an ABA swap is strongly recommended before requesting verification analysis through the authorized TI distributor or TI.com. Figure 2-1 provides an animation of the ABA swap to depict the process. The DUT is interchanged with the matching device of a known good PCB. Additional details will be provided in the remaining slides. A troubleshooting technique often overlooked during the debugging process is completion of a thorough optical inspection. Automated inspections are generally completed during the application manufacturing process. However, some PCB issues may go unnoticed by the automated tool. Low-tech assembly issues can easily be missed without a visual inspection, resulting in countless hours spent electrically troubleshooting an application. Therefore, a manual inspection should always be completed before beginning the ABA swap or another analysis technique. Utilization of a microscope is highly recommended for the optical inspection process. Examples of frequent assembly issues are bent or lifted leads, solder bridges, flux contamination, more on flux later, damaged PCB traces, and IC orientation. Visuals of typical application issues are highlighted in the top right figures, including bent leads which affect contact resistance, solder bridges resulting in terminal shorts, and flux which can affect measurement accuracy. A visual inspection is an early detection technique which can save valuable time and engineering resources. Critical inspection areas are leads and footprints, surrounding circuitry, and immediate PCB traces. In addition, it's always beneficial to obtain time-zero reference pictures of the PCB4 records. In summary, the ABA swap is an extremely powerful troubleshooting technique that applies to both complex and simplistic application circuits. In addition to verifying electrical characteristics of the DUT in various PCBs, the ABA swap helps to confirm that the problem follows or does not follow the device under test. The ABA swap helps eliminate the possibility that the issue is caused by an interaction between the DUT and other electrical components. In addition, issues with the assembly process can also be identified through the completion of an ABA swap. Resoldering a component may solve the problem. Typical assembly issues which could affect application performance are solder bridging, cold solder joints, and flux contamination. Reflowing or cleaning can result in the application functioning as expected, allowing for the issue to be closed before further analysis is performed. Slide 6 provides a detailed explanation of the ABA swap methodology. The process includes 2 printed circuit boards and 2 integrated circuits of interest, the device under test, and the control unit. The first step of the process is to record the electrical characteristics of both systems. Recording output voltage, or voltage offset of a system, is a good example. An inverting circuit is depicted in Figure 6-1. Once the data is successfully recorded, the ABA swap process can begin. Carefully desolder and remove the suspect device A from the non-conforming application PCB. Device B should be removed from the control PCB as well. Replace the TI suspect part A with a known good TI part B and check if the original failing board is now working correctly. Be sure to record the data for future records. Mount the suspect TI part A to a known good board and see if the issue is observed again. Finally, the last step will be to return device A and B to the original PCBs the units were mounted on. The final step is to confirm if the original electrical results of device A and the PCB under test remain unchanged. If device A and the PCB under test now function as expected, the ABA swap process likely fixed an assembly defect such as flux contamination or cold solder joints. Remember, it is extremely important to ensure care is taken during desoldering and resoldering processes. Proper soldering and removal of the component from the PCB is critical to the ABA swap process and for failure analysis submissions. Patience and due diligence is required to safely remove components from the non-conforming PCB. For example, integrated circuits which utilize plastic mold compound, encapsulant, may absorb humidity to some extent. Therefore, TI parts should receive a dry bake step per IPC JEDEC J-STD-033 before desoldering the component. Figure 7-1 is an example of the desoldering process resulting in delamination of the component. Delamination can be explained as the separation of two materials at an interface. For example, the separation of mold compound, encapsulant, to the lead frame of the component. In the case of Figure 7-1, the delamination can be referred to as popcorn delamination. Popcorn delamination commonly occurs due to rapid evaporation of moisture from within the package. Skipping the dry bake step prior to desoldering may result in this anomaly. The area highlighted in red represents the delamination caused by the rapid expansion and evaporation of moisture which separated the mold compound from the lead frame. This could result in lifted bond wires or impact to electrical parameters. Examples and recommendations of soldering controls can be found on TI.com. Details can be found using the link provided in this training. In addition, board cleanliness should be monitored during the soldering and desoldering process. Precision measurements may be affected by excess flux or board contamination, leading to skewed measurements. For example, excess solder flux shown in Figure 7-2 may impact electrical characteristics of an application, resulting in an incorrect reading from an analog to digital converter. Therefore, an optical inspection should always be completed prior to and after soldering a component. As discussed in the previous slides, electrical measurements can be impacted by the cleanliness of a printed circuit board. Therefore, it is important to understand common processes that can relate to an increase in PCB parasitics. Solder flux is commonly used during the PCB assembly process and board prototyping. Recall that flux is a chemical agent used to facilitate soldering of components onto a PCB. Three of the main purposes are oxidation removal from the surface of the PCB, seals out air preventing oxidation, and improving the wetting characteristics of liquid solder. It is important to remember that solder flux comes in many different forms such as resin, organic compounds, and inorganic compounds. Also, solder flux can be found in either a liquid, solid, or paste form. It is important to remember to remove excess solder flux, no matter the type of solder used. How can flux contamination result in erroneous measurements? The first example is related to insulation resistance. Excess flux impacts the overall impedance between electrical connections on the PCB. Shifts in impedance will affect electrical measurement accuracy through the introduction of parasitic electrical paths on the PCB. Flux may contaminate sensitive components like switches, mechanical microelectromechanical systems, MEMS, and contactors. Over long-term operation, mechanical components may break down more quickly. Lastly, whiskers may form between traces, resulting in potential shorts or unwanted electrical paths. In some cases, whiskers may lead to damage to the integrated circuit and/or PCB. There are a number of cleaning methodologies an engineer can apply to the printed circuit board to reduce the effects of flux contamination. A large portion of these methods include a solvent such as acetone and flux remover. Ensure all components are safe for use with the cleaning solvents before attempting to clean a PCB. Conformal coatings and flux are generally soluble when exposed to solvents. Some visual examples are shown in Figure 12-1. To improve the overall effectiveness of PCB cleaning, an ultrasonic bath can be utilized. An example of a tool used in prototyping environments is the Bronson 3510. Lastly, all coatings may not be soluble in acetone or by using an ultrasonic bath with acetone. Therefore, additional methods may be required to remove coatings to ensure the DUT is in a testable condition. Please refer to the flux supplier's technical documents for details. Why is removing flux important? Consider parasitic connections and their effects on an application from a schematic perspective. Ideally, a printed circuit board and contaminants have no impact on an application's performance. For example, Figure 10-1 depicts a schematic of a non-inverting amplifier as originally designed and simulated by an engineering team. However, in reality, electronic components and other materials create extra circuit elements known as parasitics. Let's review Figure 10-2. However, this time, please consider how the schematic would be represented with additional parasitics for each component. As shown in the real-world schematic, the schematic routing has changed greatly with the addition of parasitic components. The values of the parasitics can vary greatly depending on the cause. Some common examples are thermocouples, resistors, inductors, and capacitors. Don't forget parasitics caused by PCB assembly and soldering issues. Cold solder joints and flux contamination can also add to the overall error of a system. And don't forget, assembly issues such as flux contamination and cold solder joints can be resolved through the ABA swap process. We have seen an example of how parasitics can be represented from a schematic perspective. It's also valuable to see real-world effects of parasitic components such as flux contamination on an application circuit. Parasitics caused by flux contamination can attribute to the overall DC error of the circuit. Even worse, since flux contamination is non-ideal, the effects can be random and unpredictable. The graph shown on the right represents the electrical measurements over time of 3 examples: uncleaned system, hand-cleaned, and cleaning using an ultrasonic bath. The output voltage of the system was recorded for 60 minutes in all 3 cases. It is critical to note the output voltage over time for each example. Red represents the board when no cleaning is applied, gray represents hand cleaning, and blue used an ultrasonic bath to clean the PCB. The output voltage appeared unpredictable during the measurement process when no cleaning was applied to the board. A DC offset and a periodic spike was seen when only a hand cleaning method was used to remove excess contaminants. However, use of an ultrasonic bath to remove excess flux resulted in a smooth signal centered around approximately 2.5 volts. From the graph, it's easy to see how proper cleaning can limit the occurrence of production issues caused by contamination such as flux or assembly issues such as cold solder joints. PCBs should receive a thorough cleaning during the ABA swap process if excess flux is detected. Thank you. Please try the quiz to test your knowledge.